So, in continuing with the theme of homologous series and carbon chemistry, we're now going to look at the second homologous series of 3 for this part of the topic. Now, there are others, there are more homologous series that we will need to know about in Unit 2 in Nature's Chemistry, but for just now, we're focusing on 3. So, we've already looked at the alkanes, which were saturated hydrocarbons, all containing single bonds, carbon, hydrogen, and we drew their full structural formula. And we looked at their general formula too. We're now going to look at the alkenes. So it sounds very similar to alkanes because the alkenes are in fact very similar to the alkanes, but we have this different letter. And that different letter makes a big difference because these compounds do have one major difference about them. So we are still talking about a homologous series of hydrocarbons. So it still only contains hydrogen atoms and carbon atoms. However, this time we are talking about unsaturated compounds, unsaturated molecules. Now, what does that mean? Well, in the same way that saturated hydrocarbons contained only single bonds, unsaturated hydrocarbons can now contain at least one of what we call a carbon-to-carbon double bond, which means 2 carbon atoms bond together with more than one bond, and we call it a double bond. Okay, so a few properties then of alkenes. Like the alkanes, they're also insoluble in water, so we can't dissolve them in water. That's a physical property that links them together. As well as that, they're a bit more useful than the alkanes, because all we could really do with the alkanes was burn them as a fuel and get energy off of them, which of course is useful, but in terms of actually doing chemical reactions, that's not too diverse. The alkenes, however, can be used to make other compounds, such as alcohols, which we'll look at later in this unit, and polymers, which we won't look at until Unit 3. But for just now, it's useful to know that alkenes can be used as a starting chemical, a starting compound, in making other useful compounds, other useful chemicals. So as well as that, they contain this carbon-to-carbon double bond, and because that indicates what type of compound it is, because that tells us that it is an alkene, we call that a functional group. And all we mean by that is, if we see this functional group in that compound, it indicates that that is that type of compound. It's like a tag, it's like a badge to say that this is an alkene because it contains one of these. It indicates what the type of compound is and what its function is, if you like. So that's why we call it a functional group. And most importantly, of course, because it is a homologous series, we know that all the chemicals in this series will follow the same general formula. But this time what I thought I would do is we can try and work this out by having a look at the first few compounds in the series. So we will come back to this box and fill it out once we're confident that we know what it is by figuring it out. So just like last time, I have drawn a table of the names of the first few alkenes. Their molecular formula tells me all the atoms in the compound, and the full structural formula. Remember, that shows me all the atoms, all the bonds. Now, thinking back to last time, you should now be confident with the prefixes that are used to indicate how many carbons are in each compound, in each molecule. And if you had to have a guess at what the first one would be, have a think, because now what we need to factor in is the fact that it has to have at least one of these carbon-to-carbon double bonds. If it has to have at least one of these, that means we need at least 2 carbons. If we only had 1 carbon, we cannot have a double bond. So, the first compound in the alkene series actually contains 2 carbons. It's actually ethene, not methane. Methane does not exist, because if we only had 1 carbon, there is no other carbon for it to double bond to. So we have to have at least 2, and that's the first alkene in the series. Now again, first thing I like to do is draw in the backbone, all of the carbons, And in this case, we know now, of course, we need at least one double bond. So I'm drawing that in with the two straight lines, like a long equal sign. Now what we need to do, just like last time, dead easy, is fill in all of the other bonds to make sure every carbon bonds to 4 things in total. Now, it is different from last time because instead of just using up one bond from each carbon to bond to one another, we've actually already used 2. So to get to 4 bonds in total for each carbon, which is always what we want to do, we actually only need another 2 on each carbon. Because now, if we count through each carbon atom, we have 1, 2, 3, 4 bonds on this one, and 1, 2, 3, 4 bonds on this one. So don't make the mistake of adding in extra lines at the bottom or at the sides or wherever you decide to draw them, because that would give us 5 bonds for each carbon, and that is not allowed. Always has to be 4. Whether it's a combination of single bonds and double bonds or all single bonds, that magic number is 4. Okay? Now all that's left to do is fill those in with hydrogen. So, can we perhaps see what the general formula is at this point? Maybe, but let's just do another couple to make sure that we've definitely got it right. So the next entry in the series is propene, and now it's just the same as the alkenes. We're counting up in the same way, so ethene, propene, butene, pentene, etc., using the same prefixes, because that indicates the number of carbons. So if we have prop, remembering back to alkanes, that means we have 3 carbons, but it ends in ene this time, so that tells us that it's an alkene. So the first thing I have to do, draw in my carbon backbone, which contains 1 carbon-to-carbon double bond. And now, very carefully, I will go through and we can identify how many bonds each carbon needs coming off of it. So, I've already got my double bond for these 2 carbons. So this one here already has 2 bonds. So to get to 4, I need 1, 2 more. So this carbon's good to go. This one in the middle has actually already got 1, 2, 3 bonds. It's got loads already. It only needs 1 more to get to 4. And I will draw this in at the top. You can draw it in at the top or the bottom. It doesn't really matter, as long as it's joined onto the correct carbon. And then this last one actually only has a single bond coming off of it so far. So we actually need to give this carbon 3 extra bonds. This is the part that a lot of people will often find tricky or lose marks on. The thing you have to do before you start drawing in any hydrogens or any other atoms that are bonded to your carbon backbone is make sure they have the right number of bonds coming off of them. Okay? Just always count to 4 and you can't go wrong. Now all that's left to do is the easy bit and fill in all of the hydrogen atoms coming off of those bonds. And we don't even need to count because we've already drawn in all of our lines properly. But just to make sure, it says in the molecular formula we need 6 hydrogens for every 3 carbons in propene. 1, 2, 3, 4, 5, 6. So we must be right. Okay, moving on then. Butene, which has 4 carbons. Let's see. Let's draw in our 4 carbons. And I'll just zoom in again. And just as before, we need to make sure that we have at least 1 double bond. Does it matter where that double bond is in the chain at this point? Not for just now, but it will later on. So for just now, I'm just going to keep drawing the double bond at this left-hand side. Okay, that can change. Just like I said with the alkanes video, where there can be branches, this is another structural change that we can make, and we'll have to change the names for that change, but we will come to that in a later video. Let's just keep it simple for just now. So the rest of them have to be single bonds. We only need 1 double bond. And then, same as last time, we will go through and count how many hydrogens, we need to bond onto these carbons. So we have on this carbon 1, 2, so we need 3, 4. On this one, we have 1, 2, 3. There's the 4th. This one here, 1, 2, 3, 4. This last one only has 1, so that needs 2, 3, 4. They all add up to 4. Fill in the hydrogens. Dead easy. There we go. That's my butene molecule. Now, to figure out our general formula then, this one is actually a little bit easier than the alkanes, because if we look closely, all we're doing is, for however many carbons we have, we are simply doubling the number of hydrogens. Because it's quite like the alkenes. All you have to do is imagine that there would be 2 extra hydrogens coming off of where the double bond is, and that would make it an alkane instead of an alkene. And because the alkane general formula had a +2 at the end, all we're doing is taking that bit away. So if I actually go back to my sheet with my box, we can now fill out that the general formula is Cn, where remember n just means 1, 2, 3, 10, 100, however many carbons we have. What we have to do to that n is times it by 2 to get the correct number of hydrogens. So the alkene general formula is CnH2n. Okay, can we, just like last time, use that to work out an unknown, I wonder? Well, it should be easy. If we have octene, ene means it's an alkene. We have C8 because we know it's oct, we know our prefixes. How many hydrogens will I need? Well, if I use my new general formula, it's dead easy. I just need to double 8, and that will give me 16 hydrogens. Now if I want to draw that out, all I need to do is draw in my 8 carbons, make sure there is a double bond somewhere in there. For just now, again, keeping it to the left hand side. Make sure the rest all have the single bond and they're all connected to one another. We have to show all the bonds, remember. And then, just for quickness, I will fill in the correct number of bonds for each of the remaining carbons. We go through and count and make sure each one now adds up to 4. And then, last time, the easy bit now is drawing in all of the hydrogen atoms. And there is my full structural formula for octene, showing my double bond. Now just to recap then, what do we need to know about the alkenes? Well, they are another homologous series, so another family of hydrocarbons. This time they are unsaturated, which means, yes, they still contain just hydrogen and just carbon, but this time, somewhere in the chain, the straight chain, there has to be a carbon to carbon double bond. And because that indicates what type of compound it is, we call that a functional group. And again, we have to know the first 7 in this case, because we actually start at ethene instead of methane, because if we had methane, we wouldn't be able to have that double bond, so that doesn't exist. And we use the same naming convention as alkanes, just using the prefix to show how many carbons we have, and then to figure out the number of hydrogens, we simply use our new general formula, which is CnH2n.